Ladies and gentlemen, I'm going to say a number of things which are probably rather obvious to you. We all know that we are living in a world where the broiler has been selected and is continuously being selected for growth and for feed conversion and for breast meat yield. And we know that tremendous genetic potential is available there. But of course, we also know that this selection for intensively reared birds has a number of well, let's call it side effects, and that has generated a number of important challenges, I think, to the broiler industry. And a number of these challenges I want to list them for you, because I think this puts all what we are going to talk about this afternoon in a certain perspective. So we all know that, and that's definitely not only in Europe, but I think it's the same everywhere in the world, that there's challenges, problems with foot pouch lesions and hot burn, and there's also the problems of litter quality, and these things, I think, are linked together, especially because another issue is of course the issue of the required reduction in antibiotic use. In order to link these things together, I think that the common theme that is actually underlying all three of these challenges is actually the intestinal health of the broiler. And intestinal health is like a very important theme nowadays. It looks like everybody is focusing on intestinal health, and we want to learn more about these things, especially because in Europe we've been facing this a number of regulations, EU regulations that have considerably influenced the way people are rearing broilers, and has influenced also the way people have been looking at how to manage these animals. Since, of course, in the past it was relatively easy because I think we could, well, I call it mask a number of possible problems by using growth-promoting antibiotics. I think for many years these growth promoters have actually masked a problem which was already there. It was just not a big issue because we could keep it under control. But of course, in the EU, there was this regulation which banned the antibiotics as growth promoters from the 1st of January 2006. And I still remember that day because everybody stood up and said, right, this is the end of the broiler production in Europe. But I don't think that is the case after all. More than 10 years later, I think broiler production in Europe is alive and kicking and is doing quite well, actually. So in the meantime, of course, we see that this European regulation, which was imposed on the industry, and the regulators didn't care too much how the industry would handle this. Since then, what was considered as a big threat to the industry at that time, now it appears that this is actually a bonus, because in the meantime there's a lot of experience that has been acquired over the last 11 years, and that has resulted in better management strategies, has resulted in better feeding strategies, has resulted also, I think, in better hygienic conditions, and a lot of aspects have been steered and adapted, taking into account this aspect of, okay, we have to live without growth-promoting antibiotics. And so it turns out that the rest of the world is actually now sort of considering the same thing. It looks like in the US there's a very strong push, and this push doesn't come from the president, I don't think. It comes actually from the retailers, and it comes from actually, well, it's a kind of mentality that is being built or being induced by a number of players in this field, which I only know very superficially, but well, I suppose the next people will be able to tell us more about that. But the reason actually why we in Europe this decision was made all of a sudden out of the blue to decide to stop this from one day to another on the 1st of January 2006. The reason for that, I think, is the reason for that is that actually in those days the UK was still a member of the European Union. Well, they still are for the time being, but not for long. The UK was actually the Prime Minister. The UK Prime Minister commissioned a scientific study looking at the consequences of antimicrobial resistance, so resistance of bugs to the antibiotics, and that the conclusion of that study was that by 2050 it was estimated that approximately 10 million people would die from the problem of well, there wouldn't be any antibiotics that could cure them because they would die from multi-resistant bacterial infections. So that was an estimation. Okay, it's probably exaggerated, but nevertheless, at that point, it looks quite threatening because the number is higher than the number of people dying from cancer. So that is the background. Right. So since then, of course, because this was implemented from one day to another, we saw a number of problems coming up, and one of these problems was definitely intestinal health problems, and we saw obviously a rise in necrotic enteritis. This is nothing new because there's been, before that there were already a number of studies in the States, very interesting earlier studies in the 1980s about this entity, so this was not new, but for Europe it was something like which we were not used to, this necrotic enteritis problem. And so that's just to set the scene, and in this context I think we should understand this initiative, which I think is very interesting. So what I'm going to talk now is about the effect of valeric acid glycerides in necrotic enteritis and what actually is the mechanics behind it. But let me first give you a little bit of background information about necrotic enteritis, although I realize that most of you know this, but I think it's useful to just put this on the screen again. So we know that necrotic enteritis is quite an important entity in broilers. It's worldwide and it's considered to be economically important, and the primary cause is considered to be a bacteria which is called Clostridium perfringens, and usually you find it in around about 2 to 4 weeks in the broilers. So the lesion is actually very typical. So in cases, the so-called clinical entity, this is the necrotic enteritis which is characterized by sudden death. I mean, there's a number of animals dying, so there's a peak in mortality, and when you open up these animals, you find necrotic lesions which can be very extensive throughout the small intestine. So that's the clinical entity. But the clinical entity in Europe is actually, well, at the moment, we had a few peaks of clinical necrotic enteritis, especially in certain certain commodities, certain lines and certain environmental conditions. But most of the cases which we had which we have is actually subclinical, and subclinical you don't see anything. I mean, there's no clinical signs at all, so the diagnosis is very often missed. And but in the slaughterhouse you can see this kind of livers, with these white spots on them, and also when you happen to do necropsies of the animals, doing these necropsies at the right moment, you can find the similar necrotic lesions, but less extensive, in the mucosa of the small intestine. And so it's associated with quite some economic losses, but the problem is that the diagnosis is only, well, is missed more often, and you know, the consequences, the effects on performance of the flock is only seen afterwards. So, well, coming back then to necrotic enteritis, if you inoculate chicks with Clostridium perfringens, there's absolutely no guarantee that you will use necrotic enteritis. To the contrary, there's a major chance that you won't see anything. So there's definitely a number of predisposing factors that trigger or that open up the path for Clostridium perfringens to induce the lesions. And there's quite a lot of information already available on the predisposing factors for necrotic enteritis, and well, the most obvious predisposing factors are, for sure, are coccidiosis, and with respect to feed, we all know that high concentrations of proteins, and especially animal protein, and for instance, fish meal is a strong triggering factor for predisposing factor for necrotic enteritis. And then, of course, it's obvious that stocking density is playing a role. And I think stocking density is actually probably the major reason why in Europe we seldom see clinical cases of necrotic enteritis, but mostly they are subclinical, because we have, you know, legal restrictions with respect to the number of birds that can be kept per square meter. And so legislation is usually bothering us, but in this case it's helping us to not to have too much problems with necrotic enteritis. But it's obvious also that immunosuppression is a predisposing factor. And so for a number of years already we have set up an experimental model which is handy in the way that you can, with small groups of birds, you can check efficacy and effects of different treatments and different predisposing factors in this model. And this model is simply based on, you know, the experimental period is going from day 16 to day 24, and we start off by giving the animals quite a hot strain of Gumboro vaccine, which is triggering a mild immunosuppression, and then we switch them to a very high concentration of fish meal added to the feed, and then we use a coccidiosis live vaccine at a 10-fold dose, which is a controllable coccidiosis predisposing effect. And at that moment that we inoculated daily with a strain of Clostridium perfringens, which we have shown to be representative for the field situation, 4 days. And then it's very important, 2 days later we start doing necropsies over 3 days, and that is the period when you see the necrotic lesions. And that's interesting, I think, because if you look at subclinical necrotic enteritis, you don't see anything. Why? Because the necrotic lesions are only there very temporarily. If you wait another week, necrotic lesions are gone. Simply because the epithelium of the intestine is a very fast renewing cell type, and so lesions that develop there and that don't result in clinical disease or mortality will simply disappear again because the epithelial cells are renewed. And so in this model, we can we induce lesions in roughly like something around about 50% of the birds. So there's always a number of birds without lesions and a number of birds with lesions. And that is very handy in the way, and it's useful because then you can see whether a treatment will worsen or will protect against the development of the lesions. So the lesions are then scored. So we necropsy the birds and we score the lesions, and it's a scoring system which we did not invent. It's something from the literature, but there's actually 6 different degrees of severity. But we are not really interested in score 1, because score 1 is not typical in the way that it could be anything else. From score 2 on, of course, the necrosis is so characteristic, so pathognomonic, as we say, that this is considered to be necrotic enteritis, no doubt. So then we come to the reason why you are here this afternoon, and that's the valeric acid glycerides. And when I was approached by the company to talk about this and to work on this, actually, I think it's an interesting story. But the first thing which we did is we just plugged this into our model. And so plugging into this into the model, we used the valeric acid glycerides throughout, and with reducing concentrations. And as you can see in week 3, we are at 1.5 kilo per ton in the low dose, and at 2 kilo per ton in the relatively higher dose. And doing this, if we look at we have two aspects to look at. You can look at the percentage of animals with lesions. If you remember, roughly, the control is here. And so as you can see, there's a spectacular reduction in the percentage of animals with lesions, both with the low and the higher dose. But also there's a significant reduction in the lesion score, which means that the animals, the few animals that had lesions, the lesions were obviously less severe. So we have the two aspects that were influenced by these valeric acid glycerides. And this was quite a surprise to us in the way that this is a relatively harsh model. You use all the predisposing factors, and then you inoculate these animals with a high dose of a powerful field strain, which is actually, it's a net B carrier, the net B toxin, which is specific for necrotic enteritis in the chickens. So in these harsh models, we could see these quite spectacular effects. And so that's the reason why, from a scientific point of view, then it becomes interesting to find out now how does this work? And so we set out to try and find out the mode of action. The first thing, of course, is back to basic chemistry. And if we then look at simply going back to what we know about the acids, of course, if you go from the formic acid, like 1 carbon, all the way to C12, this is the list. And valeric acid is somewhere there, and so if we then look at these acids, it is obvious that these are acids that are short chain fatty acids that are produced in the physiologically in the lower intestinal tract of the animals by the microbes that are there. And we all know about acetic acid, propionic acid, and butyric acid. But it's known that valeric acid is also a acid that is produced naturally in the intestine by the microbes that are there. And so that to me is the major reason why we should categorize valeric acid with the short chain fatty acids and not with the medium chain fatty acids, because the medium chain fatty acids are not produced by the microbes. They are derived from the feed ingredients, or they are supplemented. So the short chain fatty acids are actually the ones that are produced by the microbes in the intestinal tract. But then when you go in the literature and you just type valeric acid in Web of Science, you hardly find anything. And if you then try and do it differently, because it's a C5, so you can also call this pentanoic acid. Even if you type in pentanoic acid, there's nothing much coming out. So in the literature, there is other people that have tried and looked in the literature as well, apparently, and they concluded that very little is known about. This valeric acid is naturally produced in the intestinal tract, but what do we know about it? So actually, when you then go further in the literature, you extend your literature search, you end up in in the biofuel industry, because apparently valeric acid is something that is of interest to people that are involved in biofuels. Nothing to do with feed or with animal production. But then there's one thing which is remarkable. It is known that the valeric acid, which is naturally produced in the intestinal tract, it is produced mostly by a microbial genus which is called Oxalibacter. And I must confess to you that when I read this first, this name didn't ring a bell to me at all. So Oxalibacter is an illustrious unknown genus in the intestinal tract that is producing valeric acid. So what can we do with this information? Well, at least we know that this Oxalibacter, it has not been cultured to date. None of the species belonging to this genus have been cultured, so it's no wonder that very little is known. But we do know that they belong to the Ruminococcaceae, and Ruminococcaceae are actually also known as Clostridium cluster 4, and most of the genera belonging to this Clostridium cluster 4 are actually butyrate producers. So this genus is related to the natural butyrate producers in the intestinal tract. There's another aspect which I think is fascinating, and that is valeric acid is actually resembling, in structure, it's resembling gamma-aminobutyric acid. And gamma-aminobutyric acid is actually a natural neurotransmitter in the brain and in the nervous system, both in the peripheral nervous system and in the central nervous system. And so the remarkable thing is that it has been shown that valeric acid can bind to the gamma-aminobutyric acid receptor. And that's interesting, because the gamma-aminobutyric acid receptor is actually a receptor that is the effect of the brain is actually a kind of relaxation, so to say. Anyway, there's a lot of effects that have been attributed to gamma-aminobutyric acid, but one of them is, I think, very fascinating, and that is that gamma-aminobutyric acid is stimulating and enhancing the activity of the regulatory T lymphocytes. And regulatory T lymphocytes are very important in the intestinal tract. Actually, you want as many regulatory T lymphocytes in the intestinal tract as possible, because these cells are responsible for tolerance to food and feed antigens. So they make it possible for us to digest food. If we wouldn't have regulatory T lymphocytes, our immune system would fight any food that enters the intestinal tract. So it's the regulatory T lymphocytes that are actually the cells that are responsible for our intestinal system accepting food proteins as a food, and not as a foreign protein that needs to be controlled and that needs to be attacked. So we want these regulatory T lymphocytes are necessary in order to avoid in humans then what we know as food allergy. People that have a problem with their T lymphocytes, their regulatory T lymphocytes, this particular population of T lymphocytes, they have food allergy. In animals also, the regulatory T lymphocytes are equally important. It's a highly conserved mechanism in the intestinal tract. Okay, so that's one aspect. That's just literature. But then we set out to do a number of laboratory experiments, and we focused these laboratory experiments in two directions. First of all, we wanted to know, is valeric acid doing anything directly to the Clostridium perfringens? And then secondly, is valeric acid doing anything directly to the mucosa, to the wall of the intestine, that may explain these effects? So the first thing which we did is to try and find out whether valeric acid would inhibit the growth and the multiplication of the Clostridium perfringens, our famous strain 56, which is used, I think, in many laboratories nowadays. So we've grown this strain in the presence of different concentrations of valeric acid, and as you can see, there's no effect, which means that this is not an antibacterial component, so it's not an antibiotic effect. Right. So that's one thing. The other thing is that the way Clostridium perfringens causes damage and causes disease is because this is what is called a flesh-eating bacteria. Clostridium perfringens is actually a bacteria that requires 11 different essential amino acids. And where does it get these essential amino acids from? By destroying host tissue. And the host tissue has all these amino acids in its proteins. So that's what Clostridium perfringens does, is actually produce proteolytic enzymes that destroy host tissues. And so proteolytic activity, proteolytic enzymes are one of the powerful weapons which Clostridium perfringens uses, and which are actually responsible for the necrosis which you can see in the intestinal wall. And so, so we set out to find out whether valeric acid would do anything to the proteolytic activity of Clostridium perfringens, and we ran gels which are actually looking at the activity, enzymatic activity. And as you can see here, different concentrations of valeric acid do not affect the enzymatic, the proteolytic enzymatic activity of Clostridium perfringens at all. So that's another thing which we can cast out of the way. So let's then go to the next. So the enzymes which Clostridium perfringens uses is one thing. The other thing which is in the toolbox of Clostridium perfringens is the so-called alpha toxin. So alpha toxin is actually a lecitinase. It's an enzyme. It's an enzyme, and you can the classical test for measuring alpha toxin activity is actually on an egg yolk agar, and so we've grown this strain on this egg yolk agar in the presence of different concentrations of valeric acid again, and as you can see here, even at 10 millimolar, there's still no effect at all on alpha toxin production. So no effect on the Clostridium perfringens growth, no effect on the proteolytic enzymes of the Clostridium, so the bug is feeling perfectly fine apparently. No effect on the major toxin which all Clostridium perfringens strains have in their arsenal. And so the next step was then to look at the chicken-specific toxin of the Clostridium perfringens. We know from previous studies that not all Clostridium perfringens strains produce this toxin. It's only the Clostridium perfringens strains that produce this toxin that can cause necrotic enteritis in the chicken. So this NETB toxin is a key virulence factor for inducing necrotic lesions. Now, it's a bit tricky because this is a recently described toxin described by a group in Australia, and the person that really did a lot of work on this is Anthony Keyburn, and he described a test to, because you want to measure the activity of this toxin. He described the test on the hepatocyte cell line. It's a complicated test. It's difficult to perform, and so what we set out is we found in the literature a paper which had looked at the sensitivity of or the susceptibility of different red blood cells from different animal species for this NETB toxin. And it turned out actually that, and that's not by accident, I think, it turned out that the chicken red blood cells, but to some extent also the duck red blood cells and the goose red blood cells are the cells that are the most susceptible to this NETB toxin. And so we developed a new test which is a quantitative test to measure the power, the toxic activity of this NETB. And as you can see, with chicken red blood cells, you have the outer zone of hemolysis, as it's called. It's really very clear that when NETB is present, these are just supernatants of different strains of Clostridium perfringens, strains that don't have the NETB and strains that do have the NETB, and you can see a clear-cut difference, especially with respect to the outer zone of hemolysis. So that is a nice test which could clearly differentiate between presence or absence or the degree of activity of the NETB toxin. And then we set out and looked at the effect of valeric acid in this assay, and it turned out that there was a very clear correlation between the concentration of valeric acid and the reduction of NETB activity. So it turns out that valeric acid has a specific effect on the specific toxin which is causing necrotic enteritis in chickens. And that to us was really interesting, because that means that the effect is very specific, and there's no other side effect to be expected. So that really, I think, is helpful to understand at least this part of the story. So that is what we see. We see this correlation, this obvious dose-dependent effect of valeric acid on the activity. So far for the effects on the bacteria. So it doesn't kill the bugs, it doesn't harm them, but it just stops them from destroying the chicken epithelial cells and causing necrosis, and that's all we need. So, but we wanted to take this one step further, and so we went out to look at the effects in vivo, and so we did a number of trials supplementing different valeric acid glycerides in different concentrations and different formulations. I don't think there's any need to go into detail there, because you'll get more information about this later on, I think. But for us, the most important thing is that we wanted to find out, is there an effect of these products on the host, and what is the effect on the host? And so these are just small trials with a small number of animals, just looking at trying to understand the mode of action. And the first thing which we did is, would this have an effect on the natural short-chain fatty acid production in the lower intestinal tract, which in our hands is of course particularly important in the ceca, but it's also important in the ileum. And so this trial was specially designed for that. But the conclusion was that it doesn't seem to affect the microbiota in the way that we did not see a spectacular effect on the short-chain fatty acids, which means that the intestinal microbiome is left perfectly okay, so it's not affecting any of the end metabolites of the short-chain fatty acid category. But still, we wanted to take this one step further, and we did the classical 16S ribosomal RNA gene sequencing. So I don't want to go into the details, but we want to know, is there any effect on the composition of the microbiome in terms of families or genera or species? And using this, we could see a limited effect, which in my opinion is of minor importance. But anyway, especially the trivalerin seemed to stimulate the Blauja group, and the Blauja group is an important acidogenic genus, and it seems to reduce to some extent the Pediococcus group. But I mean, that doesn't really explain the spectacular effects which we see in the model. So we wanted to go one step further then with another trial, and in this trial we specifically looked at the histology of the intestinal wall, because we really wanted to know, is there an effect when you use these compounds, is there an effect on the mucosa? And so we did histology, and we looked at the villus length and the crypt depth, and the villus length to crypt depth ratio. And it's clear that if you look at the control group and you look at the average, and you look at the spread, that the valerins, valeric acid glycerides, they have an obvious beneficial effect on the villus length to crypt depth ratio, which means that they are protecting the epithelial cells. When do you see an increased villus length to crypt depth ratio? When there's less damage to the epithelial cells, because then there's less need for new cells, and then the crypts become smaller and the villi become longer. And that's what we want, because the cells, the most mature cells, which are at the tips of the villi, they are the ones that are involved in absorption of nutrients. And so the longer the villi and the shorter the crypts, the better you have an absorption of nutrients and the better the intestine is functioning in terms of feed intake and the feed absorption. Okay, so that's another aspect. So we think that that is important. And then, to take this further again, I think this is to me this is the most fascinating aspect. In this third trial, we again use the same sort of experimental setup, and then in this case we looked at the what is called actually the L cells. And so let me explain this in two seconds, if I may. The L cells actually are, these are cross sections through the crypts of the epithelium. So we look in cross section through the crypts, and you can see that these are all epithelial cells that surround this small crypt lumen. And when you look at this immunohistochemical staining, so the brown stained cells are the ones that are positive, and here we stain for what is called glucagon-like peptide 2. And so these cells are the glucagon-like peptide 2 producing L cells. These cells, they look like enterocytes. So on conventional histology, you don't see them because they are in between the other epithelial cells. But they are very, very important for the functioning of the intestinal tract, because they produce glucagon-like peptide 2. And this glucagon-like peptide 2 is actually the signaling molecule. It's a signaling molecule that is secreted by these cells. It goes in the bloodstream, and it stimulates the differentiation and the multiplication of the epithelial cells. So it's very important for the intestinal health. These are actually the cells that are involved in the metabolic function, the key metabolic functions of the intestinal tract. And in which way are they stimulated? Well, you can see it here. There's several things which you could look at here, but you can see that the valerins stimulate not only the number of L cells at the level of the villi, but they also do so at the level of the crypts. And so actually this is probably explaining why we see these longer villi in these animals that have been treated with the Valerins. It is probably through the L cells, because the L cells have receptors that the so-called GPR receptors, and these GPR receptors, they sense what is present in the intestinal lumen, and signals that can bind to these GPR receptors stimulate the L cells, and what we could see is that the L cells increase in number. And so this means that they can produce more GLP-2, and this GLP-2 has a number of different effects which are all important for normal functions in the body, but the most important one to me is that they stimulate the development of the small intestine. And so they promote absorptive mucosal surface. This is not my slide, this I took from the literature, so the effects of L cells are perfectly well known in mice and in humans, but this to me is completely new in the chicken. We know now that the chicken has got L cells. Well, that was already known, but we know that we can stimulate the number of L cells by using these valeric acid glycerides, and by stimulating these L cells, it has an effect on absorptive mucosal surface, on the blood flow to the intestinal structures, on uptake of nutrients. Well, it has a number of beneficial effects. And so previously there was a group from Japan that had already injected this GLP-2 in an experimental setting intravenously, and they could show that injection of GLP-2 stimulates body weight and has a beneficial effect on feed conversion. But this was experimental injection of the GLP-2. What we do is actually trigger the natural system by adding these valeric acid glycerides to the feed. I don't know whether I'm in time, Mr. Chairman. So that brings me to the conclusions. We know that the valeric acids and glycerides have a powerful effect, and they can protect against necrotic enteritis. In our experimental model, of course, it was a partial protection because this is a very harsh experimental model. It has also direct effects on the host intestinal mucosa, and to me the most important effects are that it stimulates villus length to crypt depth ratio in the small intestine, where the absorption of nutrients take place, and it stimulates L cell density in this same area, and it has a direct effect on the NET-B expression, which is the toxin directly involved in the development of necrotic lesions. Thank you very much.